Hi everyone. Today we're going to start to looking at the theories of the atom. So today's going to be a little walk down memory lane. I'm going to go historically through our theories of how an atom have evolved, and then we're going to actually get into looking at all the different atom types and eventually drawing them up. So 400 BC. That's not before COVID. That's before Christ, or commonly now you might see a BCE, which is before the Common Era. But whether you're using BC before Christ or BCE before the Common Era, 2,000 years ago or 2,020 years ago, the time of Christ, that's sort of the pivot point. So before Christ or before the Common Era, we move backwards. So this is 400 years before Jesus. And then the old system, it'd be BC and AD, Anno Domini, after Christ, for lack of a better translation there. And so we are now to 2020 AD, or you may see in other notes CE, Common Era. Same thing. So, anyways, this is 400 years before Jesus. We're talking 2,400 years ago. Uh, Democritus, he said that all matter is made up of tiny indivisible particles called atoms. Kind of amazing when you think about it, that he recognized this. What his proof was, I don't know. I'm not a theory of an atom expert or historian, but uh, he's on record as thinking that everything is made up of tiny little particles called atoms. So that's pretty incredible. And we know that an atom is the smallest unit of an element. So if I could pop over a periodic table, we have hydrogen atoms, lithium atoms, beryllium atoms, carbon atoms, silicon atoms. So they are the smallest thing. And then fast forward to 1805. So we're looking at, just a couple hundred years ago now. So most of our knowledge of the atom is very recent. So we're a couple hundred years ago now. Dalton, he came up with what he thought was the billiard ball model. And he thought that if you can think of a billiard ball like a pool ball, when you play pool on a table, those are like a solid piece of plastic, solid all the way through. He thought that an atom was like that. It was this dense, solid sphere all the way through. What he That's wrong, and we'll get to why it's wrong. But he did have a couple right ideas. So first is they are identical for one element but different for other elements. So what he's saying is that all carbon atoms are the same. All nitrogen atoms are the same. But carbon atoms and nitrogen atoms are different from each other. And he was absolutely right. So everything on the periodic table here, each of these atoms is different from each other, but all sulfur atoms are the same. And all chlorine atoms are identical to each other. They're just sulfur and chlorine are different from each other. And he said they could be rearranged to form new substances, but cannot be created or destroyed. Once again, correct. So we can take carbon here and we can put it with oxygen and get carbon dioxide. We can take away an oxygen and we get carbon monoxide. We can put it with oxygen and hydrogen and get sugar. We can put it in a different ratio, put it with hydrogen and oxygen and get vinegar. We can take sodium and chlorine and get table salt. So he was right. You put these things together, they will react with each other, and they will form something new. You cannot destroy an atom. You can't destroy sodium. You cannot destroy potassium. And we can't make new potassium or make new sodium. We can put these atoms together and make new things, or I guess nature can pull them apart as well, in theory sometimes, but we're not destroying the actual atom. So my example there is if we take two hydrogen and an oxygen, put them together, we get water. And in theory, we could pull those apart again and we get hydrogen and oxygen again. But in that process, we haven't destroyed the hydrogen or oxygen atoms. They've just transformed into new things. Now, an electron is a negatively charged part of an atom. And Thomson in 1897, so we're looking at just 120 years ago now. He said that atoms contain negative sections to them, and he called those electrons. And he was absolutely right. They do. As the atom is neutral, the rest of the atom is positively charged. So what he said was the atom itself is neutral. He is correct. All atoms are neutral. They don't have a positive charge, they don't have a negative charge. But what he said was if it has negative sections in it, then the rest of it must be positive. And what happens is, if you look right here, a negative and a positive balance each other out and we get no charge. So if we have 20 negatives, he's saying that we would have 20 positives, making the overall atom neutral, but comprised of negative and positive parts. He was right. And he came up with what he said, he termed the plum pudding model. Now he is British. Plum pudding is a dessert over there. And so in trying to explain this to people like you and I, plum pudding model was his model. And he said the electrons are distributed like raisins in the pudding. Now this diagram, I couldn't find a good diagram offhand. This one's actually embedded in the note. I couldn't change it. But it is sort of backwards. If you think of the pudding should be positive, and the raisins in the pudding are the negative part. And I guess these little red, and this is the symbol for an electron, an E with a little minus sign. I guess those little red things are the pudding, are the raisins in this, and all these pluses are just the pudding, but they kind of look like the raisins. If we want to update this to a Canadian model, we have to think of the Tim Hortons chocolate chip muffin. So all the chocolate chips in the muffin are negative. They are electrons. All the muffin itself would be positive. And the negatives and the positives balance each other out. So the whole muffin itself is neutral. Hopefully that helps. And then fast forward about another 10-15 years and we have Rutherford. And now we're starting to get to what the atom actually looks like. So Rutherford, he came up with what's called the nuclear model. And what he means by that is an atom has a nucleus. And he is right, it does have a nucleus. So he is saying that we have a nucleus here, and around it are these electrons. So the nucleus is positively charged, and the electrons are negatively charged. And so those positive charges in the nucleus, we call that a proton. That's a positive charge part in a nucleus. Now, what he noticed too was that if you weighed the protons and you weighed the electrons, that wasn't all the weight. There was some missing weight. And so he determined that there's a third part, and he called that the neutron. So in the nucleus, you have protons, they're positively charged, but you also have neutrons. They're in the nucleus. They're not labeled here. They're in the nucleus though, and they are they are neutrally charged. So they add no charge, but they add weight to the whole thing. So in this atom here, you can see we got 4 positives in the nucleus. We have 4 negatives, 4 electrons. 4 pluses, 4 minuses makes the whole thing neutral. But to give this atom enough weight, there's also some neutral things in the nucleus called neutrons. So an atom, according to Rutherford, is only made up of 3 things: protons and neutrons in the nucleus, and the third thing are the electrons around the outside. We call these subatomic particles. So an atomic particle is an atom. Atomic just means atom. And subatomic means parts of an atom. So there are 3 subatomic parts: the proton, which is the positive charge, the neutron, which is the neutral charge, and the electron, which is the negative charge. And we can see that down here there's a little chart here. So the proton is a positive charge, and it's in the nucleus. And the symbol we use for proton is P with a little superscript or plus sign. The neutron has no charge, hence the 0. It's found in the nucleus as well, and its symbol is an N with a no charge symbol, superscript. An electron, negative charge. It's orbiting the nucleus, and its symbol is an E with a negative. Either -1 or just a negative is fine. Now, relative mass. Protons and neutrons, relative to each other, they are the same. We're just going to give them a weight of 1. So every proton in an atom weighs 1 unit. Every neutron weighs 1 unit. And you can see the electron here. In grade 9 math, we tell you that electrons have no weight. It's 1/2000th of the proton. So for our calculations, we're not doing nuclear physics here. We're going to say that electrons have no weight. So the only weight comes from protons and neutrons. Now, where Rutherford was wrong, and this is not a good picture either, is he didn't necessarily say that these electrons are orbiting. He thought there was a big cloud, a big negative cloud around the outside of the atom, and that cloud was negative. It wasn't until Bohr, a few years later, corrected him, and actually went further as well. So, and now look at this. We're only a little over 100 years ago now. So he came up with what kind of like a solar system model. So he said that these electrons do travel in orbits. You can see the orbits that they're taking. That those black lines are just showing you the path that they take. So this little electron just, I hope you like that sound effect, just whiz around the nucleus. And he says that so they travel in circular orbits, which we call a level or a shell, and they have specific energies. The further the electron away from the nucleus, the greater the energy. So here's a nucleus right here. This here is probably a lithium atom. I'll tell you why in a minute. And it has orbits. So here's the first orbit. And in that orbit is 1, 2 electrons. And then here's another orbit. And we can see 1 electron in that orbit. So let me talk to you about that for a moment. So, and we can have more orbits. We can have a 3rd orbit, a 4th orbit. We can have 7 orbits. And so the further you get away from the nucleus, the more energy that these electrons have. And electrons can move from orbit to orbit. And when they do move from a higher orbit to a lower orbit, so if we have an electron out here in the 3rd orbit and it jumps to this 2nd orbit, it's going to release energy, and we see that energy as light. So when you're doing your family behaviors lab and you saw those metals reacting and light being given off, that is actually letting you know that electrons are jumping from orbit to orbit, and you can see that. Kind of cool. Now, each orbit also holds a maximum number of electrons. So in this first orbit here, it will only hold 2 electrons. And look at this, 1, 2. We call that a full orbit, and it can hold no more. So this lithium atom here actually has 3 electrons. So here's the 3rd one. So it is found in the 2nd orbit. Now the 2nd orbit will hold 8. So we can fit 7 more electrons in this orbit. If we have more than 7 more, then we would draw on a 3rd orbit, and the 3rd orbit can hold 8 as well. So you're going to kind of have to remember that, 2, 8, 8. 2 in the 1st orbit, the 2nd orbit can hold up to 8, and if we still have electrons to place, the 3rd one will hold 8 more. The 4th one we get to 18, will hold 18. So that is that. Now, I told you this is lithium, and we're going to get to this in a subsequent lesson, but the way I know it's lithium is this. What determines that is a lithium atom is the number of protons. And I can see 1, 2, 3 protons here. And so when I go to my periodic table, this here is the atomic number. Lithium has 3 protons, so I know that's a lithium atom. Only lithium has 3. If it had 4 protons in its nucleus, it would not be lithium.